Ooh, the G factor.
Yeah, so if there's no more questions, comments, we can get back to spin 1/2 particles, which we've been discussing as another example of a n equals 2 Hilbert space. So again, the idea is that certain particles, like electrons, they have an intrinsic angular momentum, and it's something that was measured, and the explanation is, of course, quantum mechanical in origin of why that happens, but we won't explain why that happens until later. Maybe I'll mention it at the end of the class, but for now we can just take for granted that particles have an intrinsic angular momentum. So they like come along with a little spin vector. And if you think about the little spin vector as like maybe an electron is like some kind of charge that's orbiting around, and that's of course not what it is, but you can still think about it that way classically. And the last time we derived that, you know, if there's a little charge and it's spinning around with some associated angular momentum J, then it would induce a magnetic moment mu that's proportional to the angular momentum, and the constant of proportionality is the charge divided by 2m. And for an electron, as it turns out, it's not just the charge over 2m. This is a sort of classical analysis. If you do the full analysis, including effects of relativity and so forth, what you find is that instead of q over 2m, the whole thing is, the constant of proportionality is actually off by a factor of 2. So it turns out, and I mean, and this is where all the sort of difficult physics lives, in this G factor. And then there's corrections on top of that too, on top of this value of 2, coming from quantum electrodynamics. And that's the subject of quantum field theory. And one of the classic, I think, calculations is like figuring out where this thing comes from. It's the subject of quantum field theory. So yeah, but for us, you know, we just care that there is a magnetic moment, because then you can do a little experiment. This was so-called Stern-Gerlach experiment that sort of first showed this quantized nature of this intrinsic angular momentum. This is in 1921. This was done with, I think, silver atoms or something, but you have some oven that spits out particles that creates a beam, sort of particle beam. And what this experiment is you put the particle beam through a kind of a magnetic field gradient. This is along some z direction. You have a gradient in the magnetic field, usually by having some kind of mismatched poles, you know, north and south pole for the magnet with some different shapes, so that, you know, the magnetic field lines make some kind of gradient. So let's make this particle beam blue. And what was found is that as the particle beam comes through here and the particles hit some screen, what was found is that the particles deviate and hit 2 spots on the screen. Some of them hit up here and some of them hit down here, sort of symmetrically around the center line. And these are the 2 quantized values of the angular momentum along this measured z direction, minus h bar over 2 and plus h bar over 2. And the way we can understand it in terms of this stuff is just that there's a potential energy associated with any magnetic moment in the presence of a B field. It's just a magnetic moment dotted into the B field. So there'll be a force on the particles if they have a little magnetic moment. That's equal to just minus the gradient of the potential. And that's just going to be the gradients along the z direction. It's just going to be the z component of the magnetic moment times the gradient of the B field in the z direction. So, and if this is non-zero, then it'll feel a force proportional to mu of z, and then we know mu of z itself is proportional to the z component of the angular momentum, right? Or if we want to be more specific, it's gamma, this gradient times the z component of the angular momentum. So you see there's some constant, right? That's set by the gradient of the field, and also all the complicated physics involved in the gyromagnetic ratio, the gamma. And then there's this part, and this part is, from this experiment, what they found is that if you calculate all this stuff, the constant, then what's left over we find is just plus or minus h bar over 2. Those are the two values that you get when you measure the angular momentum along a particular direction. That's what this experiment does. Since mu is proportional to j, right? What are we doing here? We're measuring the z component of angular momentum. And that's what you find, that you have two observable values for this measurement, right? And remember that it's the measurement that kind of tells you what your Hilbert space should be. So if you do this experiment and you find two possible values, then you may conclude that the relevant Hilbert space for this spin 1/2 particle is a two-dimensional Hilbert space. So we can introduce immediately a basis. The basis can be just these related to these measurements, the z component of the angular momentum j, and we write these in the usual way that you can have a spin up and a spin down, and that just would correspond to states that go down in this Stern-Gerlach experiment or go up when we pass the beam through this magnetic field gradient. And so this is how you would start a kind of quantum mechanical analysis, right? You would build your Hilbert space, and of course you would normalize your basis. And we know that a particle is either going to go down here or go up here, so they're mutually exclusive states. So of course they're going to be orthogonal. And so what we want is, of course, we want a Hermitian operator that corresponds to a measure this measurement of the angular momentum, and that's the spin operator in the z direction, right? And we can sort of just write down what it is, right? We know we need to get plus or minus h bar over 2, right? So we know that when this thing, and these two things must be eigen vectors, right, of the this operator, because that's where they come from. The basis comes from the results of this measurement, right? So this thing must be diagonal in this basis. So we know that. must be diagonal in this up-down basis. And so, you know, we must get plus h bar over 2 if it's spin up. So you have a diagonal element there, and then you get a minus h bar over 2 when it's off diagonal. So this is the associated Hermitian operator for measuring the spin along that direction. Any questions so far? No? Very quiet. Okay. But we recognize now that there's nothing special about the direction of z, right? We could have put this magnetic field gradient apparatus on some kind of rotating wheel, and we could rotate this around and orient the direction of the gradient along any direction we want. And so in principle, right, there's nothing special about z. So in principle, you should be able to have, you should be able to measure the spin along any direction, right? And in general, you know, by symmetry here, if you reorient this thing, you'd still get 2 spots, right? If you take this, you spin this wheel around, you'd still get 2 spots at, you know, plus h bar over 2 and minus h bar over 2, because the z direction is arbitrary, right? We could, the beam is sort of cylindrically symmetrical, so we could say our z-axis is whatever we want. We could have measured along x or y. You still will get the 2 spots. So we know that, you know, any measurement of the spin along any n hat direction is going to be h bar over 2. And then we can define general eigenstates of definite spin along the n hat direction, right? That's what, and this would be the plus h bar over 2 eigenstate, and then you'd have minus the minus state. So that's a general thing. And what we want to know is what's this equal to, you know, in terms of, say, the z basis. That's, we want to know what's the matrix form. What's the matrix representation in terms of, say, the z-axis basis. So that's our task, and what we can begin with is, well, we know that the, what do we know? We know that the eigenvalues of this thing, right, the measured values have to be plus or minus h bar over 2. So we can factor out an h bar over 2. And then let's just say, and we know it's a 2-dimensional Hilbert space again, because there's 2 possible values for the measurement of this, of the feature that we're interested in. So in general, you could put, you know, any constants here, and let's just try to figure out what they have to be, right? So we can put arbitrary constants. These have to be complex conjugates of each other because it's a Hermitian, right? That's Hermitian. And we know that the eigenvalues of this have to be plus or minus 1. That's the only way this all makes sense physically, right? Again, we're trying to use this idea of rotational symmetry to make some conclusion about measuring a spin along an arbitrary direction. That's what we're kind of doing, just using pure thought in a sense. So if that's the case, if that's what sort of what we know, then we can, of course, write down the eigenvalue equation. And that's just, you know, a minus lambda, c minus lambda, minus magnitude of b squared. We can expand this out. You get lambda squared minus a plus c lambda plus AC minus B squared, that's equal to 0. And then you know that there's going to be two roots, lambda plus or minus, it's a quadratic equation. And we need, and it's often convenient to talk about the sum and product of the roots, because we know that we'll need the sum of these guys to be equal to 0, because we want them to be plus or minus 1. And we need the product then to be minus 1. And that's convenient because when you have a quadratic equation like this, the sum of the roots is given by this piece. It's equal to, well, this is here, maybe I'll put it a little aside over here about polynomials or polynomial equations. If you have a polynomial of this form, some highest power n and then some lower powers and up to some constant. If you solve for the roots of this, then the sum of the roots is equal to minus the ratio of the first two powers, like that. And the product of the roots, if you multiply all the roots together, this means product, multiply the roots. The product of all the roots is minus 1 to the nth power. For us, this is just 1 because n is equal to 2. And it's the constant term divided by the highest power term, like that. That's just a property of roots of polynomial equations. So for us, the sum of the roots is minus a minus a plus c, so that's just a plus c, divided by 1, because that's the coefficient of the highest power. So this is just a plus c. And we require that to be 0. And the product is just going to be the constant piece, which is AC minus magnitude of B squared, right? This is just 1, and then the coefficient of the highest power, n, is just 1. So this is divided by 1, and we require this to be minus 1. That's what we need in order for this to make any sense as a measurement of the spin along an arbitrary direction. When I say spin, I mean the intrinsic angular momentum. If it wasn't clear. So, okay. Any questions? Yeah. Okay, so if we need that, then you see that you must have A is equal to minus C. And moreover, if A is equal to minus C, then you also have A squared plus B squared is equal to 1. So you can immediately conclude that S n hat is H bar over 2. And now we can put sines and cosines, right, in order to satisfy this constraint. It's easy enough. This will be cosine of some beta, and this will be minus cosine beta. And then over here, we know that B is in general complex, right? A and C must be real again because it's Hermitian. This is real because it's a Hermitian matrix. Okay, so then, but the off-diagonal pieces can be complex. So we do the usual thing, we introduce a possible phase. And the rest of it, the magnitude has to be sine beta because you have to satisfy this A squared plus B squared is one condition. And then the other piece is e to the I alpha sine beta. And this is the general form for for the measurement of the spin along a particular direction. Any questions? Good.
I have a question.
Okay, good.
I know you went over this already, but could you go over what the? Could you scroll up one more, just a little bit, where you say SZ is equal to H bar over 2, and the subtraction of the two operators?
Yes.
How did you come to that?
Okay, so we have our Stern-Gerlach experiment, and we measure the spin along the z direction. We find two values, h bar over 2 and minus h bar over 2. So we automatically say, okay, this is a measurement, so there must be a Hermitian operator with eigenvalues plus h bar over 2 and minus h bar over 2.
Okay.
That correspond to those two states, the spin up and the spin down. And so in that basis of those eigenvectors, we know that SZ, maybe it's easier to write it just in matrix form first. It's h bar over 2, 1, 0, 0, minus 1, right?
Okay.
That's what it must be in that basis, because we know that spin up and down are going to be the eigenvectors. So this must be diagonal in that basis. So it must be a diagonal matrix, and along that diagonal, it must have the corresponding eigenvalues. And those two eigenvalues are plus h bar over 2 and minus h bar over 2. But now you just remember this very important connection between, you know, the matrix representation and then the bras and cats.
Okay.
It's very important to recognize that these are completely the same thing. This is equal to just this, right? Because this is the that 1 in the upper corner.
Yeah.
And this is the minus 1.
Got it.
In the lower corner. You have to, so that's why a lot of these homework problems seem a little repetitive. You have to really get used to this kind of connection between the matrices and the bras and cats. They're the same thing.
That makes sense. That's great. Thanks.
Okay, great. More questions. And we're doing all this in order to just understand how picking this basis along the z direction, how that's related to, say, if you were to measure the spin not along z, but if you rotated this thing around and measured the spin along some other direction. What does that measurement operator look like in this z basis? Because, you know, sometimes we'll have a coordinate system, say, along the z-axis, right? And, you know, and then we ask, well, what if you measure the spin along the x-hat direction? You know, what's the measurement operator look like for that? And that's what we're trying to derive here. And just using sort of pure thought and rotational symmetry, we came to the conclusion that the general form of this has to look like this. This is what it looks like generally. And now what we're going to do is just figure out what are alpha and beta. So far, they're arbitrary numbers. So we'll need to apply some physics to figure out what these things are. But before we do that, let's complete this thing. And you can, of course, find the eigenvalues and eigenvectors. And I'll spare you the details. I mean, at this point, you've had enough practice. You could also just stick this into Mathematica or something, but the eigenvectors are as follows. They're e to the minus I alpha over 2. Cosine beta over 2, and then e to the I alpha over 2. Sine beta over 2. And there's another one, minus e to the minus I alpha over 2. That's what they are. It's just if you take this matrix and diagonalize it, find the eigenvalues and eigenvectors, you'll get, you know, plus or minus h bar over 2, and the plus 1 will give you that eigenvector, and the minus 1 will give you this eigenvector. Okay, so let's now try to see what alpha and beta are by applying some physics. So what's the physics? Well, okay, so in general, any direction that we pick, we can parameterize it, you know, with spherical coordinates. So any, you know, any n hat will have some spherical coordinates of this n hat. There will be some angle theta away from the z-axis, and then there will be a phi angle in the xy plane. And so if you write out the xyz components of one of these arbitrary vectors, you just get the usual sines and cosines. And what do we expect? We expect that if we take, say, a measurement of the spin along the x direction, right? And let's say we calculate the expectation value, right, of this spin operator with respect to, say, a spin up prepared in the n hat direction. Well, what we would expect, right, is that if we measure this over and over again, then we would expect that if you're measuring the s component of the spin and this thing is prepared in this plus up, you know, the up direction along the n hat direction, then this better give us h bar over 2 times the x component of n hat. Because that's what it should be on average. If you prepare the spin along this direction, then if you measure the x component of that spin, right, the x component is just this. So on average, if you just do this measurement over and over again, then the expectation value of that operator better be, you know, h bar over 2 sine theta cosine phi. Similarly for all of the other components, right? If I do the expectation value of any component of the spin, right, along x, y, or z, I better just get h bar over 2 times n, you know, the component of n along that direction, where I is, you know, x, y, or z. So it must be one of these three things that you get. So in general, if I wanted to write this in vector notation, you can say that we must have, the physics tells us that, you know, for this to make any sense, that you must have that the expectation value of the spin vector, and by the spin vector, I mean a vector of operators, you know, where you measure the x, y, and z components, that must be equal to h bar over 2. The expectation value of this must be equal to h bar over 2 n hat. So if you construct little expectation values of, you know, these three components, right, then in the end you better get h bar over 2 times n hat, which is the direction of the spin, which, you know, we prepared the system in. That's the only way this can make sense classically also, right? I mean, if you have a spin oriented in some direction and you measure its components over and over again, the x and y and z components, well, then you must just get the x and y and z components of that little vector that you set up along the n hat direction. So that tells us a lot already, because since this is a kind of true fact that we must have, then you can go back to this z component basis and we can conclude that, for instance, if we take the expectation of SZ, then what do we get? We get h bar over 2. And now we have, and this is with respect to the plus, n hat. This is with respect to this plus n hat guy. Well, we just put in those eigenvectors to get the e to the I alpha over 2, cosine beta over 2. Oh, sorry. The light in my office sometimes goes out. So you put in the eigenvector, right? Transpose sandwiched between the matrix, the SZ matrix, or you know what that is. That's that 1 minus 1 along the diagonals. And then we have the complex conjugate, or this is the bra. This is n hat plus. This is SZ, and this is the ket. Again, very important to be able to go back and forth between bras and kets and matrices and so on. So this is the bra, so there's complex conjugation going on. All right, so you have that, right? And you can calculate this out. What you get is that this is equal to h bar over 2. Multiply it out, you get cosine squared beta over 2 minus sine squared beta over 2. This is when you multiply this out, vector matrix, then you do the transpose of this vector and you dot everything together. You get just the number, you get this, then using a trig identity, this is just h bar over 2 cosine beta. Now, if we go back and see what should we expect, right? What should we expect? We should expect that the expectation value of the measurement along the z direction should give you the z component of n hat. So we must have, that this cosine beta is equal to cosine theta, the direction of the n hat little vector. So we must at least have that beta is equal to plus or minus theta. Now what? So we're already almost getting there. So, one of our arbitrary coefficients, this beta, right, turns out to be related to the angle of the n hat vector away from the z-axis. That's already one thing. So now we just have to figure out what alpha is. And to figure out what alpha is, we can look at x, for instance, or x and y. And if we look at those, we know that for those, theta is equal to pi over 2, right? And since beta is plus or minus theta, then if we go back and we stick in pi over 2 for beta, we go back up here. If we stick in pi over 2 here for this beta up here, this becomes 0, right? Because it's cosine of pi over 2. That's 0, plus or minus pi over 2. So the form of this so far must look like this: 0 e to the minus I alpha. And this alpha might depend on the x or y direction, I don't know. But these are both zeros, and the sign parts are 1. So this is what it must look like for measuring along the x or y directions. And we can do the same kind of business where we take the expectation value of x and y, and we can, do n hat plus sx comma y n hat plus, and I'll spare you the algebra, but it's exactly the same as this. You put in these bras and kets as vectors, you stick in this matrix in the middle, and what you end up getting is h bar over 2 sine theta cosine, using some trig identity, alpha minus alpha x comma y. These values. So that's what we're trying to find. And we know, right, that this should be equal to either the x or the y components, right? So the x or y components are cosine phi and sine phi. So this piece has to be equal to, you know, cosine phi for the x direction, and has to be equal to sine phi for the y direction. And so there's two solutions here. Actually, there's multiple ways you can set alpha in order for this to work. But one way is you can just say that alpha is equal to phi, and then the alpha x and alpha sub x, alpha sub y in the operator are just going to be 0 for the x direction and pi over 2 for the y direction. That gives you this sine, so this becomes phi, and then these phase shifts gives you the cosine phi and sine phi for the two different directions. So that's it. This gives us the full relationship between the directions of n hat and this arbitrary operator of the spin measurement, right? There's going to be the beta piece is just the direction of n hat away from the z-axis, and these alphas will depend on the direction of n hat, and it'll be you know, for the x and y directions, it'll be either 0 or pi over 2 for alpha there. So we can write down, at least for, we can conclude now for the 3 orthogonal directions, the spin operators, right? For measuring the spin along the 3 directions. They have s sub x is h bar over 2, 0, 0, and then if alpha is 0, then this just becomes 1 and 1. S sub y is h bar over 2, 0, and then if alpha is pi over 2, e to the minus I pi over 2 is minus I. And over here, it's I to the pi over 2, that's just plus I, and these are 0. And then SZ is what we had before, it's just h bar over 2, 1 minus 1, 0, 0. And these guys out here are called the Pauli matrices. And they're denoted by sigma, you know, x, y, and z. And you can check that they satisfy various identities. One is that if you square them, they square to the identity. Another one is that their products form cyclic permutations, that if you take sigma x and multiply it by sigma y, you get I sigma z, and then, you know, similar for all cyclic permutations of the indices. So the general way of writing that is that sigma I, sigma j, where I and j are either x, y, or z, it's delta ij. So if they're the same, then this just gives you 1. This is that identity piece. And if they're different, then you get 0 plus I, and then sum over k, and you put in this Levi-Civita symbol, which is, it's a number, and it's equal to either +1 for cyclic permutations of XYZ. So for instance, x, y, z is equal to 1. It's also equal to If you take the cyclic permutations, means you permute these around cyclically, like you slide them all around each other in like a little circle or counterclockwise. So this is also equal to z x y, and then you can permute them again around, and you'll get epsilon y z x. And if you do it again, you're back to where you started. Otherwise, if it's if they're off, if it's like if one of them is flipped, so they're not cyclic permutations, and this is -1. You know, and then cyclic permutations of that. So it's -1 if it's not a cyclic permutation, but some other permutation of XYZ, and otherwise it's 0 if there's any repeats, like epsilon xxz is 0. That's what it is. It's just a handy way of writing these two rules down. These two rules are embodied in this expression. And there's other properties of it. So let's see, what else can we say? Any questions though so far about this? Just to zoom out and show what we did again. We argued that an arbitrary measurement of a spin operator has to have this form in red. We know that we can diagonalize that, find eigenvectors. And now we just want to know how these alphas and betas, which are arbitrary numbers, were related to the actual directions of n hat. And we argued that because the expectation values of these measurements have to give you the components of n hat, that constrains alpha and beta to, you know, be related to the directions of n hat. And beta is, you know, plus or minus theta, the spherical coordinate here, theta. And then alpha has to satisfy this condition that, you know, alpha minus the alpha associated with measuring the x and y directions has to give you cosine phi and sine phi, where phi is the polar angle of the n hat direction. And so then there's a little bit of freedom in that choice, actually, but the convention to get the Pauli matrices is this choice, that the alphas corresponding to measuring along x and y are these guys, and that gives you these spin operators for measuring in xyz, right, in the z basis. So again, everything here is in this spin up down along the z-axis basis, where the z is diagonal and the x and y are not diagonal, because, and this shows you that, you know, measuring along the z direction means that you don't have a definite value for spin along x or y, right? Because the x and y Hermitian operators are not diagonal in that basis. So you can't have simultaneous eigenvectors of spin along z and spin along x and y. So they're incompatible measurements. You can't, if you have a spin, it doesn't have a well-defined angular momentum along both, say, z and x. It can only have it along z. And then it'll be indeterminate along x and y. And this just comes from kind of the math of the Hilbert space combined with just some physical symmetry arguments about, you know, what happens when you measure the spin, what should happen on average, right? Okay, so hopefully that is clear. Any questions? I guess another way of writing this thing, which is common in literature, is you can put the little Pauli matrices in a vector like this if you wanted. And then what you could do is you can have an arbitrary vector now of like numbers, A1, A2, A3, if you wanted. And then there's this nice relationship that if you take this, which is just a linear combination of sigma x, sigma y, sigma z, and you multiply it by some other linear combination of sigma x, sigma y, sigma z, what you end up getting is the dot product of the two vectors, times the identity operator, plus I sigma vector dotted into A cross B. And again, B is just some vector of numbers. So this is nice, and this is related. You can show that, these two things are the same thing, really, using, the different components of the vectors. So that's another formula that's handy. And I guess the other thing is sometimes it's useful to know the commutation relations, and those are just given by 2I sum over K epsilon ijk sigma K. Usually the sum here, because of the no repeats rule, it usually just gives you one term in the sum. So like if you try this with x and y, what you'll get is 2I sigma z, like that. So that's how it works. But you'll get some practice doing this kind of thing on homework 3. What else? So these Pauli matrices are useful in their own right because we know that, for an n equals 2 Hilbert space, any operator has, 1, 2, 3, 4 entries in it. So there's 4 complex numbers that kind of describe any operator. So you know immediately that any operator you can actually write in terms of a basis of the identity plus the 3 Pauli matrices. So you can decompose any matrix into a constant times the identity plus some constants times the 3 Pauli matrices. And that gives you all 4 degrees of freedom that are required of any operator for a 2-dimensional Hilbert space. The 2-dimensional Hilbert space is basically very constrained. So that's why it's convenient to introduce these Pauli matrices and think about spin 1/2, because in some sense, you can use these as a basis for any operator. And you can think about any kind of 2-dimensional Hilbert space in terms of the phenomenology of like a spin 1/2 particle, spin up or down. And this is quite similar to polarization, right? It's the same mathematics. Instead of spin up or down, there we had polarizations in the x and y direction. But it's the mathematics is similar. Okay, any questions before I clear this? Derive the Pauli matrices. They have some interesting properties. I'm not going to prove these. This will be the subject of homework, playing around with the Pauli matrices. But they're all here, these 3 guys. The one's on the off diagonal, 1 minus 1, and the minus II. All right, I'm clearing this. And the last bit I want to say about spin 1/2 is that we can now fully we can now go back to these basis vectors of definite spin along the n-hat direction and bridge them to the spin up or down, because we already figured out what all the transformations are. And the unitary transformation, again, this is a change of basis. You go from this basis to this one. So there must be an associated unitary that connects the 2 bases. And that's given by the so-called D1/2 matrix. And it's a function of the orientation of n-hat. And it's given by e to the minus I phi over 2 cosine theta over 2 minus E minus I phi over 2 sine of theta over 2. This is right. So what this matrix does is if you do this d1/2 and you act on 1, 0, which is the up spin, right, in the z basis, then what you get is the plus n hat direction. That's how you can derive this matrix. Very easy. You just look at the components of this guy that we found just from diagonalizing that S matrix, and then you just see what the different pieces have to be in order for these two equations to be true, right? Because d1/2 acting on spin down must give you the other eigenvector. So that's all you really need to know. That gives you this piece, that's the up vector piece, and this is the down vector piece. That's it. And what's interesting about it is, look, it's really weird because if you put phi is equal to 2 pi, which should give you the same state in principle, because remember that this is the polar angle in the plane, right? This is like taking phi and wrapping it around by 2 pi. Should get back to where you started. But if you stick that in here, d1/2 becomes well, and let's make theta equal to 0, or maybe pi over 2. What's a good? Well, we could do, yeah, maybe a better example is we can also do this with theta if we wanted. So we could do theta is equal to 2 pi actually. Yeah, maybe that's easier to show this. Yeah, we can set phi is equal to 0, and then we could do theta. We could run theta around by 2 pi, which should also give us the same result. But d1/2 here, it
I thought theta was constrained to be between 0 and pi.
yeah, but you can. Yes, it is, but we can still see that there's something weird going on in terms of the sign, as we'll see. We at least expect it to be sort of periodic in some fashion, but because of these theta over 2's, it's not, right? Well, we could do it with phi. The point here is that there's this over 2 factor in this D matrix, and it means that when you wrap these angles around by 2 pi, the matrix elements don't wrap around, but they don't go back to where they started. You pick up a phase factor of -1. I'm just trying to figure out what's the easiest way to show this. Okay, maybe we can do theta is equal to 0 or something. So then you have e to the I pi over 2. This becomes this is 1. These are zeros over here, and this is e to the I pi over 2. So then if you stick in phi is equal to 0, right, you get the identity. That makes sense because that's like keeping everything along the z hat direction. But if you wrap around and you do theta is equal to 2 pi, which would give you the same thing, something bad happens, right? E to the I phi over 2 gives you a -1, right? Because e to the I pi is -1. And you get minus the identity. So that's weird. When you take your basis along the z hat direction and you rotate it around by 2 pi, you end up with a phase factor of -1. And that's related to the fact that this is a spin 1/2 particle and a fermion, which we'll see later on. And this is actually important when you talk about identical particles, as we'll see. But this is the first signature that something is not quite the same for the spin 1/2 than we had maybe for like the photon polarization. If you remember the photon polarization, we also had a rotation matrix that like connected different bases. And if you go back in your notes and you see what that looked like, so this is what it looks like for photons. Sorry, for spin 1/2 fermions. But for photons, we saw that the thing that rotated the polarization, say around the z-axis, was this e to the minus I theta sigma z operator, which ended up being cosine theta, sine theta, cosine theta, minus sine theta. And this is always equal to the identity, right? If theta is 0 or 2 pi. So very different, right? Here we get the identity for pi is equal to 0, but minus the identity with pi is equal to 2 pi. Yeah, just something to think about. There's a difference here in terms of the rotation of the basis. There's something weird going on with the overall phase. Of course, we know that the overall phase for a state vector doesn't matter if you're thinking about one particle. Our physical states are only defined up to an overall phase. So for now, it doesn't matter, but we'll see when we deal with multiple spin 1/2 particles. This will come up again. Okay. Any questions? That's all I have for spin 1/2, basically. You get a two-dimensional Hilbert space. You can orient it along any direction, and you know how the different directions are related to each other. You can rotate the bases around. And this is important. See, you have to be very careful because n hat is something that lives in 3D space, right? It's got a theta and a phi direction. It's got nx and y and z. But the state of a spin along any three-dimensional direction of spin 1/2 particle, this is a two-dimensional complex vector. And this is something that people get very confused about typically, is that the representation of the state of a spin 1/2 particle, even though the little spin can point in any direction in 3D space, the quantum mechanical state is a two-dimensional complex vector. And so you're dealing with 2x2 matrices when thinking about transforming between one state or another, or measuring the spin along different directions, x, y, z. The actual quantum mechanical states are two-dimensional vectors in the Hilbert space. And so then matrices, are like 2x2 things, but they'll have in them the 3D pieces, right? The theta and phi corresponding to the angle, the orientation of the n hat direction. So then there's a kind of interesting interplay between these orientations and then what happens to the actual quantum mechanical state. And that's kind of illustrated here, that even rotating around by 2 pi doesn't always get you back to where you started. So that'll be important when thinking about multiple particles.
That's because of the phase shift, right? Like it picks up a phase. That's why it doesn't come back even at a 2 pi rotation.
It doesn't come up because it just picks up a phase shift, which for a single vector, if we just transform a basis, and it just picks up some e to the I alpha then this doesn't change the physical state, right?
Right.
But when there's multiple particles, then it's not so clear.
Right.
Okay, and you can read in the notes posted a bit on dynamics. We did dynamics in terms of like the stationary state. You know, we did this in chapter 4. This idea that you know, if this is independent of time, then the solution to this is e to the minus I h t over h bar acting on the initial state. That's just equal to psi of t. Now, if the h, of course, for something in a magnetic field, well, the h you can write as a frequency times sz, and you know the frequency is going to be related to the gyromagnetic ratio and the gradient of the B field or the B field. But this is the appropriate Hamiltonian. It's omega times the z component of the spin. Or if you want, it's omega h bar over 2, you know, 1 minus 1, 0, 0. And now you can just plug this into here and, you know, go to work figuring out what the time dependence is. You just have to exponentiate this operator. That'll be on the homework also. But it's nothing new here in terms of the physics. It's just you can use this h to in your Schrodinger equation to figure out how a spin 1/2 particle evolves in time, the quantum mechanical evolution. But yeah, you can read about that in the notes. It's not. I don't think it's particularly important. The important thing is just recognizing that this two-dimensional Hilbert space as you know, the thing that describes the state of a spin 1/2 particle. Everything else is just applying what we already know about Hilbert spaces. Yeah. What else can I say about it? Yeah, well, I mean, the other thing is just that if your initial state is like a spin up, then of course this will be an eigenvector of your H operator because it's the eigenvector of SZ. So these guys, the up or down components in time, they just evolve by acquiring a phase of I omega t over 2. The h bars cancel, this over h bar cancels, and you just get this. This is how the two components evolve in time. What the up component picks up a minus I omega over t, omega t over 2. The down component picks up a plus I omega t over 2. And so then if you start with any, you know, you can decompose any vector, right, into an up piece and a down piece, right? Then in time, right, this just acquires the e to the minus I omega t over 2 up, and this acquires the opposite phase. So this is the general form of any time evolution for an operator. If you know how to decompose it into spin up and down, then the time evolution associated with, you know, magnetic field pointing along the z direction, it's just gonna give you these relative phases and the up and down pieces. And that's it for the dynamics. You can of course derive a lot of interesting physics just using that, but that's really all you have to know about it. You'll do this on the homework for homework 3. Okay, so any more questions about qubits or anything I've said so far before I completely change topics to infinite dimensional Hilbert spaces, which is chapter 7. No? Okay. Okay, so infinite dimensional Hilbert spaces, right? These are important because our measurements are not always two valued. We don't always get plus h bar or minus h bar. Sometimes we get, a position x, which from 0 to infinity, or a momentum or something, which can have, a continuous set of values. So for that, you can't describe that by a matrix with eigenvalues. You have to do something else. It turns out what you have to do is just extend your notion of a Hilbert space to include Hilbert spaces that have an infinite set of basis vectors. So what are some properties? You still have states, right? It's still a vector space. And you still have kets, that are elements of the vector space. You still have an inner product. It's still a Hilbert space, so it better still have an inner product. And, so you better still have this kind of business, including all the anti-linearity properties. Take the complex conjugate, you flip the bras and the kets, and you still want that if phi is equal to 0, then phi is the null vector. You still have all that. You still have completeness, which is very important. And we didn't discuss this much, but it was related to one of the extra credit problems. It's any sequence of vectors that you have, so-called Cauchy sequence, where these vectors, this is a sequence where of vectors, L is 0, 1, 2, so on to infinity. If you have vectors that get ever closer to each other, then the limiting vector, the limit of that sequence is also in the Hilbert space. So that's completeness. We won't really talk about that much, but maybe it'll come up from time to time. You still have things like Cauchy-Schwarz, that the inner product magnitude is less than or equal to the product of the norms. And the other interesting fact is that here is that all H with same dimension, that includes infinite dimension, are isomorphic, meaning that they're the same space. I can map every element. It's sort of like we had the photon and the spin 1/2 particle. It's the same Hilbert space. It's two-dimensional Hilbert space. You can directly map any state of a spin 1/2 particle to a polarization of a photon if you wanted. And so all of this is sort of the same as before. And the only difference is in decomposition of vectors. This is special to infinite dimensions, vector decomposition, right? This is where things get kind of complicated, because if you have phi, right, and you say you decompose it into a basis, right, then if it's an infinite dimensional space, then there's an infinite set of basis vectors. There's 0, 1, 2, and so on. There must be an infinite number of them because the dimension is infinite. And if you decompose any vector into, say, your infinite basis, or maybe we'll start with 1, sort of a little bit easier for notation. 1, 2, 3, all the way up to infinity dimensions, just keeps going. Well, then this becomes an infinite sum, right? It becomes an infinite sum of little basis vectors from 1 to infinity. And this is maybe not in your Hilbert space. It could be that the infinite sum here doesn't converge to an element in your Hilbert space. It does if somehow, it does if maybe somehow these the coefficient times the vector, if these little vectors here that we're adding together, if they form some Cauchy sequence, then they might, but they don't necessarily do that. And an arbitrary decomposition might not be in the Hilbert space. So you might add up all these basis vectors and sort of get something that's infinite that blows up. So when does it converge? When is sort of the limit in the Hilbert space? It's when the norm is when the norm is finite of this thing. So you have to check the norm, check the size of the vector. And what I mean by that is you just compute you just have to make sure that the terms that with very large index here, that they're kind of bounded. And so the formal condition is that for any epsilon, any small number epsilon, I can find a large enough m such that if I look at phi, and phi m is going to be the vector where we just sum over the last m elements of from m to infinity. It's like the so this is, you know, this is a sum of an infinite number of terms. If we look at the last from m up to infinity, and then we compare that to just your phi, which is a sum from 1 to infinity, then you can always find a large enough m such that the distance between phi and phi m squared, which is just going to be, if you work it out, it's just the, if you subtract off all of these, oh, sorry, I did this backwards. Sorry, it's a little bit backwards. No, this is, sorry. This is the first m terms. You just look at the first m terms, right? And you look at the difference between phi, which includes an infinite number of terms, and phi m, which is just the first m terms. Then this, of course, is the sum from m plus 1 to infinity of the coefficients of c of n squared. And this should be less than or equal to epsilon. And what does this mean? It means that this thing is in your Hilbert space, and we can form a sensible decomposition as long as, you know, the terms that shoot off to infinity can be made small, right? That you can always find a big enough m, right? That you only have to sum over the first m elements in this vector decomposition, so that everything else, the other piece of that sum from m to infinity, that piece is small, that it's bounded by any bound that you want, like say 0.1. So you know, you have to make sure that those terms in the sum that shoot off to infinity, that they become smaller and smaller in some sense, that you can always pick enough terms, finite number of terms, such that you can get this phi closer and closer to the finite sum, right? And in this case, if this is true, then you can use this Cauchy business to conclude that the limiting vector is in your space too. So that's how it works. That's where the Cauchy part comes from. A Hilbert space is complete. So if you find a sequence that's Cauchy, in this case, the sequence are these finite sums, you know, m is 1, 2, 3, 4, up to infinity. The limit of that sequence is the phi that we want, the full infinite decomposition. And as long as we can bound the finite sums in this way, then these phi m's form a Cauchy sequence, as it's called, if this is true. And then the limiting vector phi must be in the Hilbert space, kind of by the assumption that it's a Hilbert space. And so what we'll do next time is really get into this some more and see what else can go wrong. Might not be surprised to learn that operators can go wrong too, that just because you start with something that's in a Hilbert space doesn't mean that A acting on that is also in the Hilbert space. Sometimes when an operator acts on a vector in an infinite dimensional space, it pops it out of the Hilbert space. It makes it blow up. So we'll see that. And then we'll do the spectral decomposition theorem for infinite dimensions. Okay, I think that's a good place to stop if there's no more questions. You should do the quiz too.